barely see here. Okay, welcome to the Buhl Lecture. This is the 21st lecture since I restarted the lecture series in 1996. I'm Fred Gilman, the Buhl Professor of Theoretical Physics. I first met Barry Barish after I arrived at Caltech as a postdoc it's a long time ago, 1965. And there were 6 theory particle physics postdocs or visitors who were stuffed into a, at best, modest-sized room that one of the senior faculty in theoretical physics called the pig pen. And soon after arriving and meeting my fellow residents of the pig pen, as well as some of the great people at Caltech at the time in particle theory, I met the particle experimentalists, including Barry Barish, who, as I recall, was an assistant professor, I think, at that point. And he was finishing up an experiment at Brookhaven, I think on proton-antiproton goes to electron-positron. And he was also preparing for a new experiment at a new lab, the Stanford Linear Accelerator Center, or SLAC. And then our paths crossed many times. The next major time that I especially recall, and because it's a very important part of Barry's contributions to particle physics through the years, was at the International Conference on High Energy Physics in London in 1974, so almost a decade later. At that point, Barry presented the results from a neutrino experiment at Fermilab that he co-led, and the data effectively showed that neutrinos saw the same quarks in the proton and neutron that electrons also showed, and that not only did they see the same quarks, but quantitatively it was in complete agreement with our picture that was developing of the weak and electromagnetic interactions combined. That was the experimental highlight of the conference and an essential part of the talk that I gave at that conference, summarizing the many crucial ingredients that had just been assembled into what was to become called the standard model of particle physics. But even more, and over a longer period of time, our paths crossed in the 1990s during the superconducting super collider project, when Barry was the co-leader of a huge international collaboration. These were the first kiloperson collaborations in science, I think. This collaboration was going to build one of the 2 major detectors, 2 major experiments for the superconducting super collider experimental program. And this one was called GEM, G-E-M, for gammas, electrons, and muons. We pulled a man named Gary Sanders from Los Alamos to be the project manager. And included in the GEM design, what was to be the biggest superconducting magnet that was ever built. It was to be 19 meters, about 60-some feet in diameter, and 30 meters, about 100 feet long. And in fact, the largest purchase order I ever signed in my life was with Barry in 1993, I think it is, for $70 million to build that superconducting magnet. And some of you who may have noticed, I know in recent days I've even told a few people that on my desk, since in fact I've been at Carnegie Mellon, but on my desk as dean now, there's a few pieces of the conduit for that magnet. Here's one of them. And this is aluminum, of which the conduit. This is filled in at the end with copper. Actually, in the middle there would have been liquid helium, cooling superconducting wires carrying 50,000 amperes of current. And this would have been part of miles, literally miles of this material wound into this gigantic open field GEM magnet. And that was one of the main features, of course, of GEM, to get the magnet a big space, maybe half the size of this auditorium, roughly, into which you could get your instrumentation close to the point of interaction without having to deal with a magnet in between and pieces of metal that would make your accuracy in tracking and other features less accurate. But all that was not to be. The SSE project was stopped by Congress in October of '93. And I now know, even just from talking to Barry as we walked over, that by Christmas time of '93, the LIGO project, I'll get to it in just a second, was in trouble. It had failed its reviews, and it was in crisis of being canceled by the National Science Foundation, and they went to Barry to build LIGO, and he took with him Gary Sanders as the project manager for the construction of LIGO, the Laser Interferometer Gravitational Wave Observatory. So in 2000, the next time our paths crossed in a very big way, they also crossed since then, having to do with construction of, or potential construction and design of an international linear collider. But in this case, he came here to give the Buhl Lecture in 2016 years ago. And at that point, he was the director of the LIGO laboratory, which was just going into operation and trying to measure gravitational waves, which are the tiny ripples in the fabric of space and time that were predicted by Einstein in his paper of 1916, 100 years ago. And then, jumping almost to the present, on February 11th of this year, it was announced that LIGO's upgraded detectors had made the first ever observation of gravitational waves, and coming from a pair of merging black holes. So, in short, from a rather personal point of view, instead of Barry and Gary Sanders and their team having discovered the Higgs boson about a decade or so ago, they discovered gravitational waves. Not a bad trade-off, as it turned out, although very unpredictable at the time. So therefore today, Barry Barish, the Linde Professor of Physics Emeritus at Caltech and the Director of LIGO until 2006, will give us an update to his 2000 Buhl Lecture. And here it is, the encore, and then the title of the 2000 Buhl Lecture, Einstein's Unfinished Symphony, Listening for Gravitational Waves. Barry.
Well, it's a great pleasure to be back, and it's terrific to have a reason to be back. On February 1st, we got notice from the Physical Review Letters that they would publish our article that I'm going to talk about today. On February 2nd, I got this email from Fred asking me if I'd give this lecture. I, of course, assumed that Fred knew more than he was saying. He claims he didn't. I responded, I don't show my response, by saying that his timing was exquisite and that I would be happy to give the lecture. So anyway, that's a piece of history, and he's told some history. So I think I'm also going to start this lecture a little bit historically, only going back a little bit further. So we'll go back 1.2 billion years ago. Realize at that time on Earth, we were just making the transition from single-cell life to multi-cell life. And somewhere in the universe, 1.2 billion years ago, this happened, what I'll show you. And what we're seeing is a computer, not a computer simulation, but a computer calculation of the data that we've seen, which is the merger of two black holes into one larger black hole. There are features of this that you see as you go around. First, this is slowed down by about a factor of 100. The two black holes are going at a good fraction of the speed of light, which I'll explain to you. The distance between them, when I showed them at the beginning, was only a few hundred kilometers. Each of them is only 100 kilometers or so across, so not that much bigger than Pittsburgh, and but weighing 30 times the mass of the sun, each of them. And they circulate around each other, give up some energy to what we'll call gravitational waves, and as they give up energy, merge into each other and eventually become one large black hole. So that was 1.2 billion years ago. As Fred mentioned, 100 years ago, Albert Einstein had, a year before, introduced his theory of general relativity. And early the next year, he wrote a paper that predicted gravitational waves. He had introduced general relativity, and in the way he had developed it, he made an analogy to electromagnetism. And since there are electromagnetic waves, he made an analogy that carried to the prediction of gravitational waves. So he predicted gravitational waves 100 years ago. So that's when the modern part of this story begins. The experimental part of this story began maybe 50 years ago with this gentleman here named Joe Weber. He was a very superb technologist, maybe not quite as good a scientist. And he developed, having been at Princeton under John Wheeler, he developed the first detector to try to detect gravitational waves. This is a picture of his detector, which is a big bar of aluminum with detectors put on it to measure the fact that if the gravitational wave goes through this, I'll explain how in a minute, it stretches it and squashes it a little bit, or equivalently, if you hit it hard enough with a hammer, it'll ring at its resonant frequency. And these very, very sensitive detectors were to pick up that ringing, if you want, from gravitational waves. And he then put together several generations of these detectors, and in some sense, really began the experimental field, more than just in some sense. Much of what we're doing now comes from that legacy, and I'll point out three things that you'll see when I talk about our experiment. The first is that we'll talk a lot about noise. And something that we do is to calculate what noise there is that gets in the way of the detection. The first real kind of discussion of the kind of noise that a gravitational wave detector will have was really done by Weber. The second is that we, as you'll see in this experiment and people have seen, have two detectors, one in Louisiana and one in the state of Washington, and we asked that they be coincident, meaning that they gave a signal at the same time. Almost the same time exactly. He did the same thing, so he had a coincidence between one of these bars that was at the University of Maryland and a second one that was at Argonne Lab in Chicago. The third thing is that in order to calculate how significant the event is that I'll show you today, we do what we call time slices to understand background, and he actually did that in this very early experiments. There were several generations of these experiments. So that's quite a contribution. The bar sensitivity, however, is limited. You can't only make a bar so large, and it also has a very narrow, if you have a big bar and you ring it, it rings at some frequency, so it has a very narrow bandwidth of acceptance and frequency, and it can only be so large. So it's a limited technique. The technique went along for quite a while not by Weber, but people that followed him, by cooling the bar and making it quieter so that the noise was less. But in the end, once we could build interferometers, and I'll explain how they work again, as I did in 2000, then this technique was no longer of value. However, one of his students, a student named Robert Forward, actually was the first person in the US to pick up the idea, or to explore the idea of using an interferometer instead of a bar to do gravitational wave work. He then, when he left Weber's work group and went and took a job, it was at Hughes Laboratories in Southern California, and he actually built a small interferometer there before he went off to do other things. So in a sense, experimentally in the US, he was the one that started to build and to develop the first idea of interferometers. The very first idea of it for gravitational waves, as is often the case in science or in physics, is in an obscure little paper out of two physicists at Moscow State University about 10 years before. Weber developed all this, but unfortunately his science wasn't as good as all that, and he claimed detection several times. This is the first time, and it's a PhysRev article where he claimed that he saw a signal both at Argonne and at Maryland at the same time. This is a time slice. And it was proven wrong by other experimenters. And this was kind of his career, which was very mixed and somewhat bitter by the end. Okay, that was 50 years ago. 30 years ago, we actually were able to detect gravitational waves indirectly, and it was done by two scientists who looked at were using a radio telescope to look at pulsars, spinning neutron stars that spin at a very stable frequency. And they were studying a neutron star that spun at 17 times a second and noticed, and they were measuring all its parameters very carefully, and that was their research. And they noticed that this signal that they were getting was modulated about every 8 hours. The conclusion after a while was that it was modulated because actually it's a binary system, not a single system of two neutron stars. And if there's a binary system, then one's going around the other, a little like the event that we'll show today, only that isn't neutron stars. And as it goes around, there's accelerations each turn around, and as it accelerates, it loses energy by gravitational radiation. That can be calculated by general relativity, and so this slowly spirals in. Trying to detect this kind of event in LIGO, you'd have to wait 1 million years for it to totally coalesce. But basically, this is what they looked at, seeing very slowly that as it went around, its period got a little shorter each time around. And and they measured it over a period of years. This is from 1975 to the year 2000, so over something like 20 years. The period, which is shown here, got shorter by 5, 10, 15, 20 seconds, or about 1 second a year. What's shown is all the data that they took each 6 months or each year on how long, what the period was of this one around the one going 17 times a second. And the curve drawn through it is the prediction from general relativity, just taking the parameters of this system and calculating it. And what you realize is not a fit to the data. It's a curve from a calculation that just lays right on top of the data. And so this is a very important and impressive evidence that gravitational waves exist, but it was indirect in detection compared to what I'll show today. Okay, so 16 years ago I was here. This was my first slide. And 6 months ago, we saw up from the southern hemisphere over a rather poorly defined area, but over this area in the southern hemisphere, an event entered the Earth of gravitational radiation. That then came up and went through the first detector that I'll show you a little bit later in Livingston, Louisiana, and this is just the raw data that came in to Livingston, Louisiana, September 14th, 2015 at about 4 in the morning. That curve, for somebody like myself, looks extremely familiar, and I'm included in this talk a hand-drawn picture that I drew, but not for the talk here, but for other talks about that time of what signal we expected to look like, and you'll see it looks like this kind of signal. 7 milliseconds later, 2/3 of the way across the US, in Hanford, Washington, we saw this second signal. And it's really the combination of the two that we used to gain the confidence and to understand where this was coming from, for example. And you can see that to first glance, at least, they look very identical to each other. After a lot of work, we compared it with general relativity, not the first day when it came in, and this little line that I draw through it, which looks like it is the expectation we get from general relativity for what I'm going to describe as the merger of two black holes. So that was September 14th, 2015. Then we basically spent a long time trying to understand everything we could about the event, our apparatus, any kind of backgrounds we could have, and to write it up as thoroughly and as well as we could. As I mentioned earlier, we submitted that for publication in late January. It was accepted on February 1st, and we announced it, and it was published on February 11th. This is in PhysRev Letters, and this is the first figure from this publication. I'm going to come back to this figure and dissect it for you and try to let you understand what this event is. This is the event in one detector. This is the event in the second detector with the first one laid on top, moved by 7 milliseconds. This is the calculation of what you expect with general relativity for the kind of event that I'm talking about. And again here. And these are the errors showing no particular pattern, which it's not supposed to show. The event itself we call a chirp signal, which means it goes whoop. I'm hoarse today. That means that it starts at low frequency, gets higher frequency and higher amplitude, a chirp like a bird. And this is a frequency versus time plot, and you can see it gets brighter, and the frequency goes up as it goes along. So those are the two signals. Okay, I'm going to go back now and try to lay the groundwork so we can understand the event that we saw in some detail. So first, Einstein, as we said, introduced general relativity in 1915. 300 years after Newton's theory, which was itself probably the most successful theory in the history of physics. It described everything from the tides to the planets' orbits and so forth. Einstein introduced a theory that was somewhat different. The key is that space and time are united and make a four-dimensional space-time. While in Newton's theory, of course, they're separated, like classical physics. In Einstein's theory of gravity, the one problem, and the only problem that existed in 1915, where Newton's theory didn't give the right answer, was the orbit of Mercury around the sun. The orbit of Mercury around the sun, which is shown over here, comes back to a slightly different place each time it goes around the sun because of the presence of all the planets. And as it makes its trip around, one can calculate how far apart it's going to move as it moves from one orbit to the next orbit going around. That general pattern is seen in Newton's theory, but the actual calculation came out with the wrong answer, not quite the right answer. So Einstein, when he introduced his theory of gravity, which is really introducing his extension of special relativity to include accelerations and not just velocities, of course, immediately calculated the shift, the perihelion shift of Mercury, and he got the right answer. So the first success of Einstein's theory of general relativity was to get the right answer for the one thing that Newton didn't get out of his theory. That, of course, does not enough to take on a new theory after 300 years. There's often something wrong with almost any theory we have. And if you want to create a new theory, of course it should explain what's wrong, but it has to explain things that are new if it's going to be right. So this was true, and that was good. And the next thing is that what was this theory and what else can it predict? And I show this picture here, which is, think of a trampoline. Of a trampoline as being kind of a two-dimensional space, and if you put a big bowling ball on it, it would warp the surface a little bit like here. And so we have a deformation of a surface that is caused by having a massive object. So the idea in Einstein's theory is that a massive object warps space-time around it, very much like is happening pictorially here, and that affects the physics around it. So it isn't that the Earth pulls on us when we jump and fall down, as we learned as kids, but rather it's the warpage of space around us that causes us to roll in. As would happen here, if we let a marble go on the outside, it wouldn't have gone near this if we didn't have it wouldn't have gone to the center if we didn't have the ball, but if we have the ball, it'll rotate into the center. So basically, that's the geometric picture that you can draw of what this warpage of space-time idea of gravity is compared to a force. Okay, so what else could it predict? As I said, it predicted the right answer for the perihelion of Mercury. But the second feature of this theory, and it's what made Einstein a household name, is the bending of light. So what was predicted is that it doesn't matter if I've warped space-time, whether I have a massive object like a marble that I put on that, or it's light that's traveling. The light will follow the path of the curved space-time so that we can watch an object that has no mass and if it goes near another object, it should bend. So the idea that was proposed is that if you look at a full eclipse of the sun, which was done 3 years later in 1919 by Sir Arthur Eddington, he went to the southern hemisphere. Then there was a star cluster called the Hyades star cluster that went behind the sun when it was in full eclipse, and one could watch this object as it went behind and see that the light that came past the sun, close to the sun, bent as it came around it. And that experiment was done by Arthur Eddington. It actually then was published in 1920 or 21, and it's the single thing that made Einstein a household name around the world, kind of capturing the idea that light bends. So that was the second prediction. The experiment was done by today's standards. It wouldn't pass. It wasn't a 5 sigma effect or whatever we need today, if you go back and look at it, but it was right, and it was duplicated after that. Okay, actually the same effect that light gets bent going around an object can be seen if you're in the southern hemisphere. There's something called the Einstein cross, and that's the bending of light by what we call gravitational lensing, which is the same effect as it goes around an object. So this is a quasar that appears around the central glow of a nearby galaxy, and the Einstein cross, if you have good eyes, you can see, as I say, in the southern hemisphere. Okay, the last prediction that Einstein had when he came out with the theory of general relativity, or at least a few months later, was the idea that there would also be gravitational radiation or gravitational waves. The fundamental flaw and the fundamental difference between Newton's theory and Einstein's theory is that Newton's theory, when the apple falls or you jump or an object pulls on another object, has a force that's basically has no time to pass. It's what we call instantaneous action at a distance. When something happens over there, you feel it immediately. There's no mechanism by which it takes time to get to you. While Einstein's theory, the information is carried by something, in this case it's gravitational radiation, and that gravitational radiation travels at a certain speed. That's the speed in the problem for him. It's called the speed of light because that's the one we've seen, but it's the same for gravity and for gravity or gravitational radiation or gravitational waves as it is for light rays. So basically the key physical difference is that information is traveling at the speed of light, and Newton's theory, it's instantaneous. Okay, I'm only going to have one slide that has a formula on it. It's meant for those who are familiar with a particular formula, and that is that if you take general relativity, which is a rather obscure and difficult subject, you set it up in a certain way, which I won't go through here, but it's said here. The form that it has is the equation form is the form that I write here, which should look familiar to people who have seen and know electromagnetism. It's the same form which we call the wave equation, which is the waves of electromagnetism. The difference being that this is not electromagnetism, and this little thing here called h mu nu is exactly the thing that we'll measure in LIGO. So it's the strength, effectively, or what we call the strain, but the form is the same. So the form in this simple form is the same as in electromagnetism. I'll say for technical reasons, for the black hole system, it wouldn't look like this, but for the purpose of pedagogy, I'm using this, which is called the weak field limit. Then the second thing that happens is this looks like the wave equation, which means it's a wave that passes through space, and it should look like the waves we have in electromagnetism. One wave like this, and a second wave like this. The strength of it, this h mu nu, is the strength, just like the amplitude of an electromagnetic wave, it's the strength of the gravitational wave. And there's two, what we call polarizations. Just like in electromagnetism, where we have E and B fields that are perpendicular to each other. The only difference is that in this case, the two that are different from each other are not at 90 degrees to each other, like in electromagnetism, but rather at 45 degrees to each other. That's a consequence of the fact that in gravity, quantum mechanically, it's what we call spin 2, while electromagnetism is spin 1. So the experiment that we'll talk about has two different polarizations. They basically are at 45 degrees to each other. We, in principle, can separate those out. We don't, and I'll tell you why on the event that we've seen. But that can be done easily in an experiment that's fundamentally a classical experiment. We're doing the 150 years later, almost, the classical version of the Hertz experiment that showed electromagnetism, only we're doing it for, and yet, if we conduct the experiment, we can determine something quantum mechanically, and that is prove that gravity is spin 2. Okay, that's the only formula I'll use. This is the hand-drawn picture that comes from a very old slide of mine, which is why when we saw this event, it looked very much like what we've seen. I showed an incoming thing like this, a little confusion, which is the in-spiral, like the in-spiral of the event that was shown by Hulson-Taylor. They then come together in a confusing issue, which is the merger. This is the most interesting one physics-wise in the long term. And then as having come together, if you remember the picture, the little animation, as they come together, finally, it has to dissipate in some way and it rings at some frequency. And that's this last thing, which we call the ring down like this. So this general shape is what we expect, and it's what we can calculate, and it's what we saw even by eye in the picture that I showed you. Okay, before I show you that data, though, since I've referred to the Hertz experiment, you might, and probably should, ask the question, if we're going to look for gravitational waves, why don't we just do the Hertz experiment for gravitational waves? Hertz did his experiment by going down in a laboratory, creating, if you take a plus and minus charge and oscillate them, it'll make an electromagnetic wave. You go a few wavelengths away and detect the electromagnetic wave and prove that you have electromagnetic waves. That was done and can be done in freshman, sophomore labs. So can we do that for gravitational waves? An experimentalist would always want to do that because we like to control everything about our experiment. We like to know what the conditions were in the start and the end and not have something we don't understand. Of course, a byproduct in the one that I'm going to talk about is that the part that we don't understand is pretty interesting. That's a binary black hole system. But you can ask, can we do it? Well, hidden on a slide 2 or 3 slides ago, I don't think I said the words, kind of, instead of a dipole system, two charges going up and down like in electromagnetism, in order to get gravitational waves, you need what's called a quadrupole system, 4-pole system. And there's a way to make that mechanically. And we make it also in the system that I'll show you that's 2 black holes. And that is you put 2 weights on the end of a barbell, and you have a big barbell, and then you spin the barbell. So rather than 2 charges, I just spin this barbell. So I'm going to spin this barbell that I'm making here. I have a formula that I'm not going to go through in detail to calculate how big that little h is that I talked about, and put in the numbers. So I put in numbers that are kind of ridiculous, but it shows the point. Imagine that each one of these ends is 1,000 kilograms. It's pretty heavy. That this distance here is a meter. That I spin it at a kilohertz, that's 1,000 times a second. And that I go about 300 meters away. Of course, you better get out of the lab if you have something that big and spinning that much. And then I calculate how big the effect should be. And if I calculate how big the effect should be, that's spinning it, then the effect, by putting in the formula, turns out to be that little h is 10 to the minus 35. That number doesn't mean anything to you except it's very small. The number that I'm going to show is also very small, but much larger than that. So if I look at the black hole system that I'm going to report today, this same number, by putting in the numbers of the system that we're going to look at, is 10 to the minus 21. So 14 orders of magnitude bigger, and of course we're barely able to detect it with today's technology. So doing an experiment in the lab can't be done, at least now. And so we need to revert to some system in space. These are our barbells, 2 black holes going around each other, and we'll detect those. So that's the background. Now what happens and how do we detect it? So let me give you a simplified picture of what happens. If a gravitational wave goes through you, it's going to stretch you and squash you alternately with the frequency of the gravitational wave. So if it's going at 10 times a second, you'll get a little taller 10 times and shorter during 10 times during 1 second. A little bit like being in the amusement park where you go from one mirror that stretches you to the next one that squashes you, and you go back and forth. So that's what's happening, only the amount of distance is, of course, small. It turns out that we have, to do precision physics or precision science, we have a particular instrument that's especially good at measuring the difference between whether you got longer in one direction or shorter in the same direction or the other direction. And that's called an interferometer. So if I look at a coordinate system like this and I put an interferometer on it, then this is a very simple view of an interferometer. We send light in from a laser beam, hits a mirror, goes up this arm and out this arm. As long as both arms are equal in length, the light comes back, and we set them so they just cancel each other, and we then look at a detector that sees nothing. But if one arm gets longer while the other one gets shorter, they get out of phase with each other, and we get a signal in the sensor. So that's the general idea. Putting it into practice means you build some big thing like this, and that's a picture of LIGO. The reason the arms are so long, I reflected on when we talked about when I talked about the bar, and that is the size of the signal is proportional to the length. That little h that I talked about is proportional to the length. We're going to measure a difference in length that it expanded over a length. And so the longer we make it, the better. The practical length, without having to deal with too much curvature of the Earth, is about 4 kilometers. So we made a system that's about 4 kilometers long. Otherwise, it looks like that picture of an interferometer. In here somewhere we have, I'll show you more details, we have mirrors and a laser. It goes down one arm, goes down the other arm, which goes off this picture, comes back. If they're exactly in sync, they cancel, and our little photodetector sees nothing. If one of the arms gets a little longer than the other one, then we see a signal. So that's the idea, and we have to monitor that extremely carefully. This picture is in Livingston, Louisiana, one of our 2 sites for LIGO. It's a commercial pine forest, so they cut down these pine trees around. We own just a little strip of land here, along here. And if you know Louisiana, it's a little bit wet. And so along here, you'll notice this is all water. In order to build LIGO, we build it up on a berm like you do a road if you build it in Louisiana so it doesn't flood. To get the dirt to build the berm, to put it up a little ways, we put it up at the 500-year floodplain. Then this immediately filled with water, alligators, fish, and so forth. And then it was a place that hunters like to come because they actually like the alligators and fish and so forth. This is the second one. And for the purpose of the lecture today, they're absolutely identical. We compare the signal in one with the signal in the other, but you can see it looks quite different. This is in Hanford, Washington. Hanford, you'll recognize probably from the words, is a big Department of Energy nuclear site, which has reactors and has a lot of nuclear research. They own a huge amount of land just outside of Hanford, Washington, and basically we sited this on their land. Obviously no pine trees, it's hard, high desert, and the conditions are quite different. So we have 2 detectors, one in Hanford, one in Livingston, Louisiana. Two institutions at that time, one here, Caltech, one here at MIT. You might ask how we end up here and here. It's politics. At Caltech, when we submitted the proposal at the beginning, the idea was we took a sample site because you couldn't tell the government where to build it, and it was near Edwards Air Force Base, high desert in California. And in MIT, our MIT collaborators looked at a site in southern Maine, a short drive from MIT. We didn't propose that exactly, but it was in the first communications with the NSF, who decided that they would take over the siting and ask us to be responsive to expert questions about the technical features of the siting. And then it ended up here and here, and Fred would realize that there was a senator in Louisiana, who was very influential, we believe, in this decision, and was very supportive for us. Okay, notice the distance apart. It's 3,000 kilometers apart, and if I take the speed of light from here to here it takes about 10 milliseconds. So if I have light that starts here and goes to here, it'll take 10 milliseconds be here, 10 milliseconds before here. If it's coming this way, it'll be 10 milliseconds here before here. And if it's directly overhead, it'll be the same time in the two. So if we're looking for gravitational radiation, which should move at the speed of light, as I said earlier, then we look for these to have a signal that's plus or minus 10 milliseconds from each other, which is going to be true for the event that I'll show you. This is our laboratory. Basically, we make a vacuum pipe. This is the biggest, as far as I know, the largest high vacuum system in the world. It's, the pipe itself is 1.2 meters in diameter, goes for a total of 16 kilometers, 4 kilometers in each direction, and is at high vacuum, 10 to the minus 9 torr or better. And that is because the light going back and forth down this, we can't allow to have very much scattering of the light on any residual molecules, because if it scatters off residual molecules, it can find a longer path. It can scatter out to the walls, come back to hit the mirror on the other side and find a longer path back and be delayed. So we basically have to keep this at high vacuum, and also we have baffles and ways to protect the sides of the tank. This is just the construction of the pipe, and this is a small enclosure that we put over it to protect it from the elements. There's the elements. That's a DOE cowboy driving across the... Inside, the working part of LIGO looks a little bit like this. So this is where this central place is where the mirror is that splits the beam and sends it down the two long arms. And you'll notice all the little ports all over the place and this thing here. What we've done is try to create as flexible a laboratory as we can create. These chambers are very large compared to a small mirror that we might put in it. And we built this from the beginning so that we can put in it a variety of sensitive ways to make our instrument as quiet as it can possibly be. When we built LIGO at the beginning, we didn't know how to build the instrument that I'm going to show you today in detail. Conceptually, we kind of had the idea, and we were able to convince the NSF that we could do it, but it took years of R&D between then and now to develop the techniques and to put them in the detector. If we didn't have the flexibility to put it in, we probably could have never done this because it would be too expensive. So one of the innovative things about what we did was convince the NSF from the beginning to make an infrastructure, which is what I'm calling this, that was flexible enough so that we could develop detectors that would get to the limit of what's possible in a 4-kilometer long site. So we did that, and we built that. That gives you a sense of what it looks like. And now we have these interferometers. So the light comes in, it splits just like the little picture I showed, and goes down one arm and goes down the other arm. But you'll notice I have a hanging mirror here and here, as well as the ones on the ends. These are the two lengths that I'll measure. But the reason for the second mirror is that each of these arms we make, and I'll use a technical word, Fabry-Perot interferometers. What that means is that we turn these arms into resonant cavities where the light gets trapped in the cavity and bounces hundreds of times. That means that we've artificially created a much longer path length for the light than just the 4 kilometers. And that is, as well as we can, again, use the space. And so we have hanging mirrors here, 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 and here. Appreciate that they're hanging. They have to be hanging to be free masses that we talk about for gravitational wave radiation to move them or to measure a distance. And yet, if you reflect on anyone who's actually used an interferometer and gone into freshman or sophomore laboratory, if you don't go up to an optical table and put your mirrors down very tightly on the optical table and then look for your fringes, you probably see nothing. So we have this extra problem that we're not allowed to put it down on an optical table because we want it free from the Earth. We don't want the Earth to shake it, and we want a measurement that's just our measurement that's free from the Earth itself. So by creating them as hanging masses, we basically have hanging pendula, but the pendula frequencies are much lower than the frequency that we'll look for gravitational waves. A pendulum moves at 1 or 2 times a second. we're going to look at gravitational waves at 100 times a second. So basically, we just have to control it at the lower frequency. We then have finally a photodetector here. We put the light coming back this way and this way, out of phase with each other, and this sees no light nominally. The distances are important because this is now the accuracy that we need to have in order to make the measurement. And reflecting back on when I showed you the barbell, I said we had to do 10 to the minus 21. Well, what does that mean? We have to be able to measure a difference of 1 part in 10 to the 21. We have a length of 4 kilometers. So to do that, we have to measure a difference in length of 10 to the minus 18, 1 part in 10 to the 18. 10 to the minus 18 meters. How small is that? That's 1/1000th the size of a proton. So if you want to disbelieve the experiment, that's the first thing to realize, is that we're claiming that we're measuring a difference in length of 1 part in 1,000 the size of a proton. So how can that even be possible? It's not possible on a single measurement with a single photon or light beam. It's possible because we have a very high power laser, and we multiply the light a lot by bouncing it back and forth. So it's the power of statistics. If you make a measurement enough times, you get a very accurate answer if you keep all the conditions under control. So basically, even though the fundamental shape of the mirror is not as good as 1 part in 1,000 the size of a proton, on the average, if we do it enough times, which we do, then we can measure to that accuracy. So that's the trick. Now, I have to go back to what Weber talked about and tell you what limits this device. And this is where experimentalists like I spend all our effort almost, is trying to minimize the things that limit this and to understand them within the data that we take to make sure that we handle them as well as we can. So there's a lot of things that limit us. These are the key ones. So the first is, I mentioned already, residual gas scattering. So we have to keep this at very high vacuum in order to keep that small, and there's still going to be some molecules, so we have to have whatever methods we can have to test, to understand, and to be able to determine what the level is of residual gas scattering. That's the first one. I told you how we control that. The second is the laser itself. And the laser itself, like this little laser I'm using here, is a pretty stable object. We all know that. It has a very nice beam of light. It's got a unique color, green in this case. And so we think of it as being very stable. It's nowhere near as stable as we need to do this experiment. So we build a special laser. It has a particular wavelength. In our case, it's in the infrared, 1024 nanometers. And then we have to work very hard with a lot of very special techniques to stabilize it much better than a laser normally is in wavelength and amplitude fluctuation, so that its color is exactly a particular color and that its amplitude doesn't change. We do that by a lot of special techniques, which I won't go through here, but the final laser that we have is probably this world's most stable laser. The next thing is just the test masses themselves. Even though they're hanging from wires, something has to touch the ground. And so the shaking of the ground affects the test mass. Of course, if it shakes and moves, then it's a moving target for us to hit. So we have to minimize this as much as we can and understand it, and I'll show you where that comes in. It turns out to be fundamentally what limits us at the lowest frequencies. The next is just something we call KT noise, related temperature or thermal noise, or Brownian motion. And that is the movement of the molecules themselves within the mirrors or the test masses. And so the fact that we don't cool these test masses, which would be a nice thing to do, but technically very hard, and it might happen in a future detector, we basically have molecules that are moving around and so forth. That creates what's called thermal noise, and I'll show you where that comes into the spectrum. And lastly, we get to noises that end up being the limit of how well we can do. And I just show one example of that, and that is what we call it quantum noise. It maybe is a little bit of a misnomer. But the idea that I told you before is we keep increasing the number of photons. You think if we keep increasing it forever, can we get a better and better measurement? The answer is no, because as we increase the number of photons, that increases the pressure that those photons exert on the test masses themselves. There's fluctuations in that. So we have a trade-off between what's called shot noise, which is how many photons, and radiation pressure that limits us. So that's another limitation. That just gives you a sense of them all. I show them on the schematic graph here, which is frequency going, that's sensitivity going this way. This is that same little h. This is the magic 10 to the minus 21 in here. And this is frequency this way. So all these different curves on here are more or less schematic, but they're those different noise backgrounds that I talk about. The highest envelope that I can make for this is the final sensitivity of the device. Sensitivity is best down this direction, and it's as far as you can go this way and this way. So you notice that we're limited by 3 different technical reasons in 3 different frequency bands. At the lowest frequency, we're limited by what I call seismic noise, which is the shaking of the earth. That's what limits how low we can go in frequency. At the highest frequencies, the technical term that's used is shot noise, but it's basically how many photons we have, or photostatistics for a particle physicist. And in the middle frequencies, by what I call thermal noise. And so first thing as an experimentalist is that this is not great, because as an experimentalist, usually you have some background that's limiting you and you use all your energy to reduce that. Here we have 3 different ones in the 3 different regions, so not ideal for an experimentalist. We have to control all these ones below as we try to minimize these. Notice where this whole frequency band is and why we use the word listening. This goes from about 10 hertz to 5 or 10 kilohertz, just like your ears. So that's why we use the word listening, and in our control room, we take the signal that we see or don't see, and we convert it to an audio signal just so the operators can hear what noise there is. It's not the signal because we're not good enough for that yet, but in the control room itself. It's not an accident that that's the frequency band that we're sensitive to. We're sensitive to that frequency band because by evolution, our ears have picked the quietest place to work for us as a listening object on the Earth. That is, at the lowest frequencies, if we could go down lower in frequency, the Earth shakes so much that, because this thing's going up as frequency to the 4th power, that we would be bothered by too much noise. At the very highest frequencies, our ears cut off because we have to sample too fast. You have to sample faster and faster at the highest frequencies. This is exactly the same. At the lowest frequencies, it cuts off because the Earth shakes too much. At the highest frequencies, it gets worse and worse because we have less and less what we call photostatistics, less photons in the same piece of time that we need to develop it. So the device, although it's nothing to do with hearing, basically has the same features because it's living on the Earth as our laboratory as we do with our ears. Okay. Now I'm going to start showing the results and the data and show you what we've discovered. We ran, since the time I was here in 2000 until about 2010, in off and on, and got our sensitivity, which has the shape like the graph I showed you before that looks down, down, and up. It's just a slightly different scale. This is seismic. Look at the thin line along here and up here. The actual achievement of what we called the initial LIGO is this top colored band here. And that is basically what we proposed, and except at the very lowest frequencies, which had more noise than we liked just due to what goes on in Louisiana, we achieved the goals of what we call the initial LIGO. We then started to do an improvement program, which is what I'm going to report on today. And the idea was to improve a factor of 10 in all 3 of these regions that we talk about. The seismic, by making better seismic isolation. How do we do that? By adding what we call active seismic isolation. That is something that senses the movement of the Earth and corrects for it. Better at high energy, high frequency by having a more powerful laser, therefore more photons. And in the middle area by having better test masses and suspensions to reduce the amount of thermal noise that we have. The goal was to do about a factor of 10, which you can see from the scale. This is a factor of 10 in all three regions. And the factor of 10, I'll point out, basically tells us how far out we can see to look at events in the universe. A factor of 10 sees 10 times further out. 10 times further out means it sees 10 to the 3, or 1,000 times more of the universe, or galaxies in the universe. So we gain very quickly if we can improve. Because of that, we stopped part way. So anyway, this red curve here was just putting in the very first stages of what would be the improvement, which was easy to put in to keep people busy while we built the rest of it. There's a lot of people. We have a collaboration that's worldwide and has about 1,010 scientists that authored the paper that I'll show. We then installed our very sophisticated systems, which I've told you in words and I won't say anymore, except to just give you a sense from a picture of how complicated. This is the laser, so it's a lot more complicated than the one in my hand. And it's stabilized for the reasons that I said in frequency and amplitude, and is a very special wavelength. It's 1024 nanometers. It's called a neodymium YAG laser. And this is it on its table. This is the masses, the test masses themselves, the mirrors. These are the best mirrors ever made in the world, I think. They basically are 40 kilograms each. They're thick and heavy, which we want them to be, so they're stable. And the surface of them is as good a mirror as are made for the best telescopes, what we call super mirrors. And on top of that, we put 30 layers of a dielectric that is designed to reflect the light at exactly 1024 nanometers, neodymium YAG laser. So when I look at these, I'll show it from the side in a minute. When we look at these, the eye sees right through them. They look like clear glass, beautiful, beautiful clear glass. But for 1024 nanometers, they reflect. This is then the same mirror, and you can see through it here, the same mirror in its pendulum, but now we made a multiple pendulum. It has four different levels. I won't take you through the details, but the bottom one is free of any instrumentation. It just hangs there, making it as quiet as we can possibly make it, and we try to control its position by moving these upper ones. That's tricky. It took us a while to develop that, but that's the scheme. And this is a big, heavy, beautiful test mass made out of, by the way, fused silica. And lastly, the third part of the instrumentation to improve this was to add something you can't see in any detail, except that you can see there's a lot of stuff here, to add a very sensitive system of correcting elements, active correcting elements for seismic noise. We detect the seismic motion in the three transverse directions, X, Y, and Z, and the three rotational directions, and we then correct for those. And that reduces the amount of shaking by the factor of 10 that we need. So this is the result. The top line, by the way, these vertical lines that are on here you should not pay any attention to, but I'll tell you what they are. They're basically the fact that you build anything that has legs, wires, whatever it is, there's what are called resonant frequencies. And so the wires that this hangs from have resonant frequencies, the stands have frequencies, and so forth. We know what almost all these lines are that are shown here. They're very narrow. We notch them out. They're stable, they're always there, and they're just part of the technical thing, and they just look funny on these plots. So this is the plot of where we were when we turned off in something like 2012 or 2013, and then we turned back on with all this improved instrumentation. When we turned back on, we presently reached, for the event that I'm going to show you, a factor of 3 improvement at high frequencies. At low frequencies, because we put in this active seismic isolation, it improved a factor of 100. The rate for any real event goes as the cube of these, So this is 27 times more sensitive than when we turned off, and this is 10 to the 6 times more sensitive than when we turned off. And that's why this event that I'm going to show comes down in here. We couldn't have seen it in our previous detector, not until we improved it. Notice we're not down to this line yet. This is to come. So the improvements that we've made should bring us down to this bottom line, another factor of 3 roughly below where we are now. But we've decided to take it in steps because of the fact that the rate goes as the cube. So by improving a factor of 2 or 3, then we take a data run, and then we'll improve again. So for example, we haven't yet put in a high power in the laser, which will go up to 200 watts, and is presently running at about 20 watts. For the next run, we'll probably go up to 50 watts. But we want to do these things systematically and slowly, so the process of getting all the way down here, which has been scheduled from the time we build it, will be another 2 or 3 years. Anyway, so this is where we are, and we started to take data last fall. So now I'll talk about the discovery. You've got all the background now to understand it all. Last September in 2015, we were in the final stages of preparation for the very first science run for advanced LIGO. We called it O1, Observational Run Number 1. We were due to turn on in mid-September. The very last step we call an engineering run. And that's just a very last step for us, where all the responsible people have to write off they're happy with their system, and we can keep it stable for the next 3 or 4 months that we're going to take data. In contrast to most experiments, we can't, I'll show you why, but we can't fool around with it and change it once we're running. So we have to keep it stable because we rely on stability in order to assess what the probability is of anything we see being real. So this last engineering run is a bit of a misnomer, but it's basically meant to be, is there anything you want to touch? Touch it now, because you're not going to have a chance again. And usually we turn on to this engineering run with the idea that no one's going to change anything. It's just the last check. So we're in this engineering run 3 days into a 5-day run, and we saw the event that I showed you before. I'll show it to you in more detail in a minute, which we call GW 150914. That translates into gravitational wave 2015, September 14. So that's our nomenclature. If we ever get good enough to see more than one in a day, we call them little a, b, c, d. So, this event was identified not only by I and by our online operators, but in our computers within a few minutes. So it was identified very quickly. We responded by officially declaring the data run started instead of engineering. But what that meant for us is we had to keep all the settings fixed. And we calculated immediately that in order to understand the significance of this event, we had to run for what I call 16 live days. By live days, what I mean is that both detectors have to be running at the same time with the right sensitivity for 16 days. That took us, I think, 32 or 33 days to get that. So we were at more or less 45 or 50% efficient. After the 30 days, or getting the 16 live days, then we could assess how significant this event was, which is one of the first things that, and maybe the first most important thing we had to do to see how important, how useful this was. Even though it looked so beautiful, we didn't have any experience that we might see funny events that look like this too. So we took this 30 days of data. Then we reported on it, as you saw in physical review letters, in February of this year. Now, just as a footnote, we continued taking data after the 31 days. The original length of time for this run was meant to be until January from September. That's 4 months, more like 120 days. And we ran until January 2016. And we're just in the final process of putting together our results from that. And I anticipate that they'll be released by June 1. So we're very close to releasing that data, our results, and it'll probably be another, if it slips, it's not going to slip very much from that, but about June 1. Okay, so now let me start to show you what we saw. So let's look at this picture a little bit. This picture here is the raw data that we see. Only it's what we call bandpass filtered. That is that we look at it between 35 and 350 hertz, the frequency that we're looking at, and ignore the other frequencies. The time difference between this one and this one, by sliding them and seeing where they fit best, was 6.9 milliseconds. And in this row is the numerical relativity waveforms. So let me step back for a second and say, what do I mean by that? It turns out that in order to calculate what you expect for gravitational waves, we've got to invoke general relativity. We can invoke general relativity and calculate it without too much difficulty for something like this Hulse-Taylor picture where I showed you the line going through the data. We can also do it without a very complicated calculations if we have light objects. So if we had seen spinning neutron stars coalescing, it wouldn't have been very difficult to do the next step that I'll talk about. But to do it for heavy objects, it gets into the part of general relativity that takes sophisticated and difficult calculations. Since we don't know the masses of the two objects that we're looking for, we don't know their spins, we don't know their directions, what we do is take all the possibilities that are kind of within our sensitivity, and we calculate each one and make a template which we compare with the data. There are 250,000 templates that we have to develop. So that's and use. So there's two aspects of that. How do we calculate 250,000 templates and do them right? That required a breakthrough in being able to use computers to calculate general relativity by numerical relativity. That breakthrough happened after I was here last. It happened in 2005 or 2006 in the way the calculations were done. And now, so if we had seen this in 2003, we couldn't have done the lines that I draw through. But since 2005 or 6, the way to calculate on a computer numerical relativity has been developed. And then since then, of course, all the waveforms have been developed by different teams and so forth. So we have a choice of very good waveforms to use. And they're, in a sense, a big part of the story that I'm telling is that the numerical relativity community, that's not us, they're really theorists, developed the waveforms that we were able to adapt and use. So anyway, we take and calculate them for all these different angles and masses, and then the one that fits best is shown here, and the one that fits best for the other one is shown there. Then the next question is, how significant is this event that we saw? I hinted that the way we tell the sensitivity, the significance is by comparing what we see in the detector in Louisiana and what we see in Hanford, not when they're within 10 milliseconds of each other, but when they're out of time with each other. So that at any random time in Louisiana, or all through the month at the different times, and all through the month at the different times in Hanford, we compare and ask where we get the best coincidence connection between the two, and what's the probability, which I haven't written down for you, but there's a way to calculate the probability. These are the candidate events. This is a statistic on how significant. The bigger the number this way, the better the fit of the two. And they come down here. This is 10 to the 0, so it's one event. So there's one event here, there's one event here, and then there's an event here. This is the one we're going to talk about. And the event right here may well be a gravitational wave, but we're not claiming it because we don't know how to really tell events yet that aren't standing way out here. What's shown here is a line that goes down to something like 10 to the minus 5 or 10 to the minus 6. It's basically taking the data from one of the interferometers, comparing it with the other one, and sliding the bins, the 15 millisecond bins. And we see that we get down here events that come out to about here is the total. And if we remove this single event here, we get the light line that goes down here. So what this is, this tail, which never comes out to here, what that tail is the real event in one of the two detectors coincidence with noise in the background. If I remove the real event, there's nothing that comes anywhere near this kind of statistic. So this stands way, way out. The statistic then, by looking here, is greater than 5 sigma, and that's just limited by how much data we took to do the background. It could have been much higher than that if we went further. This event stands out. In each of the two detectors, by far, it was the noisiest, what we call the noisiest or the biggest event. So in each of the detector, if you just look singly over 1 month of running, this single 10 millisecond slice was the largest by far in both of the detectors and had exactly the form that we expect from general relativity for a binary in-spiral system. Now let me speak to this a little bit, because why do we even think that this might be two black holes? And let me give you a qualitative picture for it being two black holes. Yeah, I'm at the end. This is two black holes because of the bottom picture here. And it's the last thing that I want to really make sure you know. What's shown is velocity going up and time going this way. And it's this merger of the two objects. And what you see is the separation is in some units which we call Schwarzschild radius, but it's 100 kilometers or so. So it starts with them about 300 or 400 kilometers apart. They merge together to be only about 100 kilometers apart. So you have to imagine two objects, each of them 30 times the mass of the sun, but only apart by a few hundred kilometers. And each of them then can't be bigger than about 100 kilometers. And their speed is on this axis, and it starts at about a third the speed of light, and by the time we stop measuring it, it's up to more like 6/10 the speed of light. So basically, the objects have to be extremely compact, and then we fit the data and get the parameters that are shown here. So I'll summarize the parameters and make a few other comments and then stop. We have two black holes that when we fit it, each of them about 30 solar masses, 30 times the mass of our sun. The sum of them adds up to 62 solar masses, the final object. And the final object is spinning. It's a technicality, but not at the highest spin that's allowed by general relativity. And it's a long ways away. It's 410 megaparsecs where it started. That's the 1.1 billion light years that I referred to. There's a couple of conclusions which I'll draw for you. Even seeing these black holes is new. So even from this one event, with all the telescopes, all the ways we've looked at the sky, we didn't know that there were black holes that were 20 times the mass of the sun around. So not only did we first see that there are massive black holes, what we call stellar black holes that are 20 times the solar mass or more, these are 30, but they're found in pairs, and the pairs can merge in the lifetime of our universe. That's all new. There's already thought about what that means in terms of the progenitors. How do you make a heavy enough star to decay and give this? If there are such things, it has to be very special because stars like to blow themselves apart if they're big and heavy. And so some conclusions are that if there is a progenitor, it has to be low, what we call low metallicity. My point here is only that we've seen new astrophysics already with gravitational waves based on our first observation. The second is we can use these events and hopefully in the future to do very significant tests of general relativity. The test that I show here is only to look at that waveform and realize that the waveform that I showed would be affected if the gravitons or gravity was made out of gravitons and they had some mass. Because if they had mass, then at different frequencies it would travel at different velocities, and that would change the waveform somewhat. And so by testing and looking at the waveform we have compared to giving it some mass, we're able to set a limit of about 10 to the minus 22 eV on the mass of the graviton. I show those two things just to say the science that'll come out of this in the future is both astrophysics and general relativity. Lastly, let me just talk about localization because that's where it's going in the future. Looking at black holes, We don't expect to see anything in our telescopes or electromagnetic counterparts, but for other sources that we hope to see with gravitational waves, we do need to point to the sky better and then ask what electromagnetic telescopes might see. This is how well we saw this particular event. It's in the southern hemisphere. It's a great big it's a great big wide thing. As we go into the future, we're going to have more gravitational wave detectors around the world, including one of our own in India, and that'll change this picture. So the picture that is shown here is the picture we have now. This is it evolving in time, but let me just go down to here. Once we get into roughly 2022 maybe, and there's a new detector which we're building in India, a detector in Italy, a detector in Japan, then we can tell the position in the sky to something like 20 degrees square. Not as well as astronomers might really love, but pretty good, so that one can anticipate that this can become part of doing what we call multi-messenger astronomy, that is using the gravitational wave signal and the electromagnetic signals together. Let me just end by saying that this is nowhere near the end. We know how to improve LIGO. I indicated that. There's an improved detector being built and implemented in Japan. It has the features of being underground and being cooled to low temperatures. And the Europeans have ambitions to build something that's considerably bigger than LIGO, shown here, 10 kilometers in a triangle. And that's gone through a lot of studies in Europe. So it's going to take decades before we get anywhere, but we're nowhere near the end of a field. We're at the beginning of a field, in that we'll see how to develop gravitational waves to detect all the things that I was talking about, but even at different wavelengths. So in the future, we're going to have a gravitational wave detector in space, probably by 2030. There's ways to go to even lower frequencies, and just like for the electromagnetic spectrum, in the next whatever century, I expect that gravitational waves will be a completely new way that we'll have information about our universe. So in a sense, I think that this seminar is an encore, as Fred called it, but I think it's also a prelude. Thank you. Yeah. When we built LIGO, these two instruments for LIGO, we had to make a decision very early. And that decision was whether to make the two instruments parallel to each other or at 45 degrees to each other. And we could have done that by just rotating it on one of the sites, and we had to choose. The reason we actually chose to make them parallel to each other, so the data that we have now has no information on polarization. If we had made them 45 degrees to each other, then we could disentangle the polarization. The reason we chose that is because we knew that for the first observations of gravitational waves, as was part of our convincing story, was to have really the same signal in both and not different signals in the two. And knowing that the future detectors in other parts of the world will help us do the polarization. So the polarization will come in future measurements, but not as long as we're limited to these two LIGO detectors.
Another question? Yeah, way back. How many other events are of interest to you right now, and what's your take on putting one of these things in space called Linde?
Okay. The first part of your question I can't answer, or I'm not allowed to answer, but I can bracket it for you. I'll just put a curve up while I talk to the other thing. I think I have it here. What's shown here is the probability, just from probability, not what we really have, that we'll see more than 0 more events, in other words, more than 5 more events in the present run when we finish analyzing it, it comes out 85 or 90%. So I told you within a month, we'll report on this event. The probability, just calculating probabilities, is there should be more events in there, but not necessarily. It's possible there won't be. But one or two more, maybe. As we move to the future, it'll be tens of events in the next few years, just from trying to predict it from a single event. LIGO in space, that's a very interesting future, basically. And that is, it's called LISA. It began as a joint project by NASA and ESA. It's three, you can almost see it here, not very well. It's 3 satellites in a triangle, with a long distance. The sensitivity is a totally different sensitivity band than LIGO, 10 to the minus 1 to 10 to the minus 4 hertz. And they've done the first test mission, which they call a Pathfinder, which seems to be working quite well. It takes a long time to do things in space. The present program is to have a mission for LISA itself in something like 2032. Whether the US will be part of that is still an open question. That's up to NASA.